Brilliant. Thank you, Steve. Thanks for inviting me today and giving me the opportunity to present some of my work with the people today, with the people who are interested within application of QbD in continuous process. And thanks for the kind introduction. So I think, just to start with, I'm going to talk about the application of QbD in continuous process and presentation today. So if we think about actually our process, we can represent it as it is now in the schematic. That means we will end up with a continuous process here with a individual step all linked together. We will have some material input, which will be one of the variable, and we will have obviously the process input, which will be a function of all the different parameters of the process. And these can be monitored, obviously, and can be look back to actually some of the instrumentation, but through the instrumentation we have to actually make some adjustment on the process, or we can actually directly go for a strategy of pass and fail. So we are feeding, so we have those time of addition, we are steering, or we are mixing anyway overall. So we have the mixing time, we have the mass transfer, we have the heat transfer, we have the KLA. So all this physical rate needs to be integrated within the overall simulation to have a better understanding on how it works. So if we zoom on one of these box, we will end up having this view there. So which are actually our process variable and which one could become critical. So if we have a closer look here, you can see we have preparation of feedstock. So that means we can have different input of material, different supplier, different batch number or different lot. We can have during the preparation of them different dilution or different stoichiometry during this preparation. We can have as well different feed time or different feed rate, so which will affect actually the stoichiometry and the material balance within the reactor. We have actually a jacketed system to cool or to heat. So that means we will end up with different heating or cooling capacity based on the different type of reactor, different material of construction, different property of the media inside the reactor, or different property of the media for your heating cooling fluid. And obviously, as I said, we will have the kinetic. And I think it's the overall picture which makes sense together. But we needed to actually evaluate if one of these technology was more appropriate to reach right yield and right quality. And it's why we run the same exercise as you've seen before with the different variable of parameters, that mean temperature and flow and stoichiometry. We run the same for the reactor. Just in this case, actually, we end up with different variables. We end up having a type of reactor, that means mixing time. We had different heat transfer. We had different material of the reactor, which generate overall to the overall heat transfer, and mixing time, dimension of the reactor, volume of the reactor, geometry, as I said, all these parameters could be screened. And knowing that from this, we will have an input, and from then we can do the heat balance. We'll have an input, which will be the enthalpy of reaction, and we will have the output, which will be the heat, which will be which can be withdrawn by the reactor to maintain the temperature at the set point plus minus 5% as being actually our acceptable range. And we can screen all these parameters specific to the characteristic of the reactor. And actually we can see that we have, based on impurity 1 and 3, some acceptable range here. And based on this acceptable range, we can define which type of reactor are suitable for the chemistry to hold this set point. And like that, we are not blind thinking that we know about the chemistry and hoping for the best that the reactor will suit our need. We are able upfront to put into relation the chemistry and the reactor. So this is what actually the process look like overall. That's a scheme, but I can't disclose too much, unfortunately. But we had the starting material coming into the first one with some bully, which was split in two in two streams to actually maintain the temperature below the maximum threshold. 5 CSTR, overall 50 milliliter. It's a really small reactor. It can hold within a shoebox. After we have made in stainless steel to enable actually good conductivity and a good heat transfer coefficient. After that, directly telescope to the second cascade of CSTR with SO2 added there in one shot. We could control the temperature there. We have solid all over the system here, which can be well suspended. And at the end of this 10th vessel, once again, this vessel here is 5 times 10 milliliter. It's in the borosilicate because we had actually some corrosion issue, or if we were using stainless steel. And Asteroid was a bit expensive, and glass was making the job. So we as well try to be a bit pragmatic within the material we order and the construction of our system. We have to make it as cheap as possible. And that material is directly overflow within a stop and flow system when we had by portion SO2Cl2 to do the chlorination. We had all this system together with the pump, the reactor, the transfer line within a 2x2 meter footprint. So really, really small.
How do you think you would have approached this if you didn't have the simulation tool to use on the project? You know, did the simulation actually save you time, or how do you view that, Flavien?
Yeah, I think simulation or process understanding and process modeling didn't save me time. I think it saved my life. Yeah. I think it was necessary. I think, you know,
Right.
let's be honest. I think he had to be done that way. We had such a complex chemistry that we could have probably tuned it in the lab and find some nice sweet spot to run it in the lab. After, when you have to transfer it to larger scale, if you don't understand the criticality of the parameters in relation to the characteristic of the reactor, you have to run kind of a DOE on scale to find your sweet spot, and you don't necessarily have the material all the time. So I think here the advantage of simulation is that it prepare you about the scale up already by integrating all the different elements at scale, reactor and reaction. After, yes, it takes a bit of time, but to be honest, it doesn't take so much time. We have the chance that we have the expertise in terms of process simulation. So actually building the model together it was not necessarily long, and we had good chemists as well. And the partnership between these actually enabled us to put together within less than 6 months and pilot within less than 6 months the entire process.